Even should I plan for going about an hour or so?
Yes. You can share the screen.
Yeah, just a sec. Okay, are we good?
I think Max was eating. Okay. Maybe we can start. What do you think, Lukasz?
Hi.
Okay. So welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math and Physics seminar series. It is our great honor to have a Professor Lukasz Fidkowski from the University of Washington. He'll be speaking about his recent work with Wang and Matthew Hastings on gravitational anomaly of 3+1 dimensional Z2 torical gauge theory with fermionic charges and fermionic loops, self-statistics. Let me remind the audience, please feel free to interact, ask questions during the talk. So thank you. Let's welcome Lukasz. Thank you.
Great. Thanks so much for the invitation, Juven. So yeah, so I'll be talking about some work that I did with Zhengwen Ha and Matt Hastings on this topic of gravitational anomalies of 3+1 dimensional Z2 toric code with both fermionic loops and fermionic charges. So, oh, there we go. Okay. So one thing that I want to sort of say from the get-go is, the results that I'll be discussing are results about gapped Hamiltonians on lattice systems, or results in the context of this menu qubit model. in the context of condensed matter. There is an analogous story here in field theory, and I'll mention some aspects of that story, but I really want to emphasize just from the beginning that the results that we have concern classifying gapped phases of lattice Hamiltonian. So in fact, I'm going to have the first couple of slides be just kind of a very broad overview of sort of the difference between gapped phases of lattice Hamiltonians on the one hand and field theories, because both can be classified. You can classify gapped phases of lattice Hamiltonians, you can classify field theories, but what is the relation between them? So let me explain a little bit about that. So right, so the thing that we are going to be interested in here is as I already mentioned, lattice Hamiltonians, typically gapped lattice Hamiltonians, and it is in this context that we're going to define the notion of gapped phases. Okay, so gapped phases are certain equivalence classes of gapped lattice Hamiltonians. Now, in classifying gapped phases, so defined, it is sometimes useful to use results from continuum quantum field theory. So basically, the idea is that there are certain responses in these gapped lattice phases that can be nicely packaged, nicely encoded in certain mathematical structures, which are just topological quantum field theories. And so then one can sort of leverage the mathematical classification of topological quantum field theories to obtain at least a partial classification of gapped phases of lattice Hamiltonians, which is the thing that I'm going to be interested in. So that's sort of one way that field theory appears. And just to sort of harp on this a little bit longer, so here I've sort of drawn, on the left side, sort of the lattice world of gapped lattice Hamiltonians, and the right side, the world of continuum TQFT. So, so just so we're all on the same page, when I talk about gapped lattice Hamiltonians, I'm really thinking about this many qubit model. Okay, so I'm really thinking about many body systems as being defined in this many qubit model living on a lattice. So the sort of canonical example is spins living on some kind of a lattice. So here, there's a Hilbert space. A Hilbert space is a tensor product of site Hilbert spaces. There's a Hamiltonian, which is a sum of local terms. There's a notion of locality. One can also define symmetry action. So if you have a global unitary symmetry, it acts on site. It acts on each of these individual spin Hilbert spaces. And then the global action is just given by tensor product over all sites. So this is sort of a familiar world of the many qubit model. So in the context of this many qubit model, let me just call it maybe the lattice model. What do we do? How do we probe Hamiltonians? Suppose you have a gapped Hamiltonian. How do you probe it? How do you define an invariant of a gapped lattice Hamiltonian? Like, what do you actually do? Well, one thing that you can do is if the Hamiltonian is gapped, you can create localized excitations above the gap and then do certain things to them. So, the most famous example is braiding anyons. If you have a two-dimensional intrinsically topologically ordered Hamiltonian, you can make these excitations above the gap, which cannot be created locally, so they have to be created with string operators, and then you can braid them. Okay, you can braid them. That's the thing that you can do, and you can define sort of braiding data in this way. On the continuum field theory side, things are a little different. So on the continuum field theory side, instead of having a lattice Hamiltonian, typically what you can consider is space-time manifolds. And so the idea is here really that these space-time manifolds don't have to be of the form some space across a time direction. They can be sort of more general space-time manifolds. Here, for some reason, I put down I put down an immersion of the real projective plane into 3D. There's no reason I did that. I just sort of did that to illustrate, that you can have non-trivial spacetimes. But what you have is non-trivial spacetime manifolds. So you can sort of probe the theory on non-trivial spacetime manifolds, and the thing that you can compute is this exponentiated action. It's exponentiated action. So symmetries can also be incorporated here. They're incorporated in this setting as principal G bundle. So G symmetry is incorporated as an additional data over principal G bundle, and then the exponentiated action can depend on this principal G bundle. So it's a very different setting. Whereas in the lattice, you can make these local, the way you probe it is you make localized, you stay in flat space, but you make localized excitations and you probe them, you do something to them. On the field theory side, you never really make excitations above the gap. Everything somehow still stays in the ground state. It might be a topologically degenerate ground state, but somehow you stay in this ground state subspace. And instead, what you do is you probe the theory by putting it on non-trivial space-time manifolds. Okay, so it's just different ways of probing things. So despite, so one thing I want to emphasize, despite the fact that these are really different worlds in this sense, it turns out that predictions, made on the continuum field theory side turn out to often be borne out on the lattice side. And specifically, this is the case in the case of invertible and SVT phases. So these are phases without anyons. So, there's this nice classification of invertible TQFTs by Fried and Hopkins and others. And the predictions of this classification, the field theory classification, have often, have always so far been borne out on the lattice side, although sometimes in unexpected ways. Okay, so there's sometimes, there was this story with the generalized double semion model that I talked about maybe a year or two ago, where it turns out that the predictions of TQFT, the predictions on the invertible field theory of the invertible field theory are borne out on the lattice, but just with maybe not with Hamiltonians that you might not expect. So one such prediction that I'll be focusing on in this talk is the prediction that in 4+1 dimensions, so 5 space-time dimensions, 4+1. So I'll always say 4 space plus 1 time, with no symmetries. There's a prediction sort of from the field theory side that there should be a non-trivial invertible phase. Okay, so this is the phase which, again, at the level of field theory, has the action built up entirely out of Stiefel-Whitney classes. The action is just 1/2 integral of W2 W3 over the manifold. Okay, over your 5-dimensional orientable manifold. So this this action, or the exponentiated action rather, is the thing that discriminates between the trivial and the non-trivial cobordism class of oriented manifolds in 5D. So it's sort of well known that for 5-dimensional oriented manifolds, there's precisely one non-trivial cobordism class, which is the cobordism is oriented cobordism is Z2. So there's the manifolds which are boundaries of other manifolds, and then there are manifolds which are cobordant to the so-called Dold manifold, which is a certain fiber bundle with fiber CP2 over S1. So there's basically two cobordism classes, and this action that I wrote down here is precisely the thing that distinguishes between them. So the exponentiated action gives you a +1 on the trivial cobordism class and -1 on the non-trivial cobordism class. Okay, so that's just field theory. Field theory predicts that there should be a non-trivial invertible phase. So the question, on the lattice is basically, is this borne out on the lattice? Is there a non-trivial invertible phase of gap lattice Hamiltonians? What is its Hamiltonian? And maybe more importantly, what is the quantized lattice invariant? Like, what do you actually do on the lattice? What do you measure? What experiment do you do to see that you're in this non-trivial, basically to distinguish this non-trivial invertible phase from a trivial product state, let's say? What do you do on the lattice? That's the question that we kind of, so this is sort of the set of questions that we addressed in this work. So how would one probe a 4+1 dimensional invertible phase? Suppose I gave you a Hamiltonian and I claimed, okay, this is the Hamiltonian for this non-trivial 4+1 invertible phase. What can one do? How can one probe it? What one cannot do is, braid anyons, simply because this is an invertible phase, right? So this technique that we have for intrinsic topological order, where we just make anyon excitations and braid them, and sort of extract data about the phase through the braiding statistics of the anyons, that's not available here. So it's already sort of a difficult problem. However, we do know what to do in these cases, what we can do is we can look at the boundary of the theory. Okay, so one very well understood class of examples of theories that have no anyons in the bulk are these so-called SPT phases, symmetry protected topological phases. So these are phases that have no anyons, but they do have a global symmetry. And the one way, so one way that these phases can be probed is by braiding symmetry defects. But additionally, what one can do is one could look at the boundary of an SPT phase, and the boundary turns out to have an 't Hooft anomaly for this global symmetry. So if one can find some kind of a lattice way of diagnosing this 't Hooft anomaly, then that one can sort of use that to diagnose the bulk phase. And this is a very well-known story. Of course, even without symmetry, in the case we're looking at right now, there is no symmetry. But even without symmetry, invertible phases still have anomalous boundaries. And what happens in that case is that the boundaries have a gravitational anomaly. So basically, the low energy theory that lives on the boundary cannot be realized in sort of a many-qubit model, a standalone many-qubit model in the lower dimension, in the boundary dimension. So, canonical example of this is just the chiral edge of an integer quantum Hall phase for fermions or E8 phase for bosons. These are boundaries that have a gravitational anomaly, and by that here I just mean that they can't be realized in a one-dimensional many-qubit model. Although that's it's not completely obvious, but that turns out to be true. So the question that we want to ask here is that can we probe this putative 4+1 dimensional invertible bosonic phase by looking at its boundary? So so of course this is, again, I really want to emphasize this is, Juven, the question?
Yes, I have a question. Maybe this question might also be appropriate for Professor Danfrey. So the question is that earlier you mentioned the correspondence between this lattice Hamiltonian bosonic phase classification and also the invertible topological phase classification, maybe by Hopkins by cobordism. So I was wondering, say, whether the 3D example that without symmetry, whether the cobordism class may be defined in a more subtle way, because we require the sum of the Z class, which is a free part. And that Z class, we know in lattice model, we can have the so-called E8 quantum Hall states that you mentioned in the previous slide. Actually, you can go back to the previous slide. Yeah. And so we know that's a generator which has chiral central charge 8, and it also has non-trivial framing anomaly, because the A is not the 0 ma 24, I suppose. But I wonder whether in the cobordism classification, the generator from maybe the cobordism group kind of a prediction, is that the generator is also the E8 quantum Hall, or is that the 24? Which means I was wondering whether there's a framing anomaly.
Oh, okay, that's a good question. I don't actually. I don't know the answer to that. It's not going to be relevant to the rest of my story, but if anybody wants to chime in.
I don't know whether
it's a good question. Yeah, it's a good question.
Because I saw at some moment I saw that they agree, but for some reason I kind of wondering whether the cobordism group can calculation can give rise to this E8 quantum Hall.
Yeah. Okay. Yeah. I mean, good question. I don't know whether it's the E8's the generator or 3 times the E8 or.
Yeah, that's right. That's
even precisely like how to phrase that question. I guess I don't even. If the field theory just gives you a Z, then like you don't necessarily know.
Yeah.
Yeah. Okay. Yeah. So let me maybe not say too much about this question. I don't think I have anything particularly intelligent to say about this question. But
if other people have comment, please.
A lot of what?
I say if other people have comment, can speak out. Otherwise, we can just go on. But I'm puzzled by it is slightly whether this generator in the cobordism class is 8 ma 24 or is it 0 ma 24?
Yeah,
3 times, 3 times different. Yeah. Anyway.
Yeah.
Thanks.
No, that's yeah. I'm not gonna have too much to say. Okay, so right, so so one. Right, so I should say that all these questions that I'm talking about have been investigated in the context of field theory, and there is a sort of story in the context of field theory. There's as far as Z2 gravitational anomaly, as far as gravitational anomaly in 3+1 dimensions, there is sort of an obvious candidate for a low energy theory that has that anomaly, has non-trivial anomaly. And this is the all-fermion QED, all-fermion quantum electrodynamics. So this is well, let me step back. So certainly compact quantum electrodynamics, compact QED is a theory that can emerge out of a three spatial dimension lattice model. So you can have an emergent, you can have lattice Hamiltonian models in 3D, where the low energy description in terms of this compact QED, and the charges can be either bosons or fermions. One can certainly rig up models like that. What's sort of less trivial and more anomalous is the case where both the charges and the monopole are fermions, and therefore so is their bound state. So that turns out cannot be emerged out of a 3D lattice model, out of a standalone 3D lattice model. There's actually an argument for that by Wang, Potter, and Senthal, sort of a surprisingly subtle argument, which I'm not sure I understand all of its. I think it's correct, but I'm not sure I understand all of its sort of subtleties. So there's an argument that this all-fermion QED is anomalous at the level of lattice. Of course, at the level of field theory, there's a well understood argument, but at the level of sort of lattice models, there's an argument as well. So that means that, okay, it can, if it can live anywhere, it can only live at the boundary of a 4+1D invertible phase. Okay, but then how do you construct the 4+1D invertible phase that at whose boundary this thing lives? It's not so clear. So this is also, I want to say that this is not the approach that we'll take. We will not focus on the all-fermion QED. Somehow, that's a theory that's just not particularly amenable towards the kinds of exactly solvable lattice model constructions that we have. So instead of focusing on all-fermion QED, what we're going to do in this talk is focus on a Z2 gauge theory, which we obtained by Higgsing this all-fermion QED. Okay, so condensing double charges, condensing pairs of charges, which are bosons. So there shouldn't be any obstacle to doing that in all-fermion QED. So we get a Z2 gauge theory, and then the question at the level of the lattice is, what is anomalous about this Z2 lattice gauge theory? We know it has a fermionic charge, but there's certainly non-anomalous Z2 gauge theories with fermionic charges that can live in a 3D lattice and write down explicit models, but somehow this thing should be anomalous, should be non-trivial. So the question is, what is non-trivial? What experiment do you do on the lattice to see that this thing that you obtained from Higgsing the all-fermion QED, all-fermion compact QED is actually non-trivial. So before I sort of get into the details of our various constructions, let me kind of summarize the results that we have. So the results of this talk are going to be that we've defined a new lattice invariant, which we call the loop self-statistics, for this for 3+1D fermionic toric code. So in other words, or fermionic Z2 gauge theories. So in other words, whereas 3+1D Z2 gauge theories with bosonic charges, it's believed that there's only one class. 3+1D gauge theories with fermionic charges, 3+1D Z2 gauge theories with fermionic charges actually split into two classes, and one of them is anomalous. So I would like to point out that there's this really nice work by Theo Johnson-Freud that does this in the context of fusion one categories and field theory, which which basically is very nice, and it kind of motivated us to sort of study this problem on the lattice. So I want to emphasize that what we found was sort of a lattice prescription, a lattice invariant, or a lattice experiment, lattice quantized invariant that actually allows us to distinguish between these two fermionic toric codes. You know, it was sort of an open question of like, what experiment do you actually do on the lattice to distinguish between these? So furthermore, okay, so we defined this lattice invariant. Furthermore, we were able to build an exactly solved model in 4+1 dimension, 4+1 dimensions, which precisely realizes this anomalous fermionic toric code and its boundary. And we're able to prove that this is indeed a non-trivial invertible model and that it's Z2 classified, which means that two copies of it stacked together can be transformed via a shallow depth circuit to a trivial state. So we have the story in 4+1D on the lattice as well. I also want to mention that there's this nice work by Yuan Chen and Poshen Sin that came out in the same video as our work, which sort of covers similar ground. They also built an exactly solvable model of this. So we checked that this exactly solvable model that we built does indeed realize this anomalous fermionic toric code. Okay, so this is just a summary of results. I haven't told you how to define any of these things, but this is just sort of a forward-looking summary of results. So let me tell you how to actually get any of these things. So, before I tell you how to define this loop self-statistics, let's just sort of re-examine something simpler, which is just ordinary point particle statistics. So you might think this is completely trivial. Why am I talking about this? But I just want to emphasize that, in order to define exchange statistics, let's just say you want to diagnose whether you have fermions or bosons. Let's just say you're in 3D with emergent quasiparticles, which can either be fermions, bosons, and you want to tell which. Okay, so how do you actually tell whether something's a fermion or a boson? This is not entirely trivial. You say, oh, just exchange them, but of course, it's just exchanging them. If you actually implement that on a lattice by moving these particles with string operators, there's all sorts of non-universal phases. So you have to be careful about canceling out non-universal phases. You have to design an experiment that cancels out non-universal phases. So the way that you actually do this, and I'm being a little pedantic here, but there's a reason for it. It's because this naturally generalizes to the case that I'm interested in, the case of loops. So the way you actually define, on the lattice, define an experiment that measures these statistics, one way to do it is to first define these 6 different configurations. So these are 6 different configurations where the identical particles that you want to exchange are located at these various positions of this sort of T-junction. Okay, so first you define these states. You pick these states, and what's going to be important for the way that I define this invariant is that these 6 different configurations, 6 different configurations have to be locally identical. So in other words, if I have a configuration where the center is occupied, for instance, like here and here, and C2 and C6, I demand that these are actually identical as states in the vicinity of C2 and C6. So that means that the reduced density matrix here and here is identical. That's sort of important for for canceling these non-universal phases. You really want to kind of hit these various states that look locally identical. So you define these configurations. That's step 1. Step 2 is you define these string operators that move the particles, either M1, M2, M3, which basically move them from the center out to the periphery. Okay, so you define these string movement operators, these string operators. Particle movement operators, which are string operators, and then you consider this sequence of 6, of this composition of these 6 string operators. So this performs, if you just kind of track this along, this performs an exchange. It's just this T-junction exchange. And the nice thing about defining things this way is that you get something that where non-universal geometric phases cancel. So what do I mean by that? Well, what I mean is that applying this process, you start and end at the same state. So you end on some, the state that you end on is some phase times the state that you begin with. This composition of these string operators just amounts to a phase when acting on this state. And the claim is that that phase is independent of the various arbitrary choices that you made in defining this invariant. And one nice sort of way to break down the dependence on the various arbitrary choices is first to think about, for a fixed choice of these configurations, this phase doesn't depend on the particular choice of string movement operators, of these string operators. And one can check that carefully, but essentially it amounts to the fact that every time you see an M, like an M1 here, there's a corresponding inverse. Okay, so basically, if you were to sort of redefine, take a different string movement operator M1, which particle movement operator M1, which also moved a gauge charge from the center out to this lower left endpoint. It would basically, its action would have to differ from the action of the old one just by a phase, and that phase would cancel between here and here. Okay. Now these don't exactly act on the same state, but the point is that the state that they act on is basically locally the same. The only difference is in the position of this second fermion, which is sort of far away from where all the action happens. So this phase computed in this process does not depend on the choice of these string operators. So that's the first step. And the second step is to just show that it's actually independent of the precise choice of these configurations C1, C2, C2, C3, C4, C5, C6. So in other words, I can maybe move these fermions around a little bit. It doesn't really matter exactly where they sit. I will still obtain the same value of this invariant if I move the fermions. Okay. So the nice thing about defining, going to all this trouble to define an invariant like this is that once you have an invariant like this, you can really leverage it to classify phases of gap lattice systems. Okay, because the point is that this invariant stays the same under shallow circuit equivalence. So shallow circuit equivalence is sort of the thing that you want to think about when you're classifying phases of gap lattice gap lattice Hamiltonians. And so the point is that if I have some state that's in a given phase and I apply a shallow depth circuit to it, shallow depth quantum circuit of local unitaries, that's still in the same phase. That's sort of part of the definition of phase equivalence. That's still in the same phase. And so it's very clear that this invariant is going to be the same for those two systems, because basically what you can do is you can apply your shallow depth circuits to all these configurations, and you can conjugate all your string operators by this shallow depth circuit, and it's just you've conjugated everything, so you still compute the same overall phase. So that's why such an invariant is nice. It immediately gives you something that can be used to classify gap lattice Hamiltonians. Okay, so with that sort of pedantic introduction, let me now say what we did, which is we were able to define this notion of loop self-statistics. Okay, so this is you can kind of think of it as a generalization of this T-junction process to one higher dimension. So the natural way to generalize the T-junction geometry to one higher dimension is to again have a central vertex, which I've labeled for clarity in blue here. All the edges emanating from it are also for clarity labeled in blue. There's no reason other than sort of geometrical clarity that they're labeled in blue. But so we call that vertex 0. And now we have 4 exterior vertices. So in the case of the T-junction in 2D, we had 3 exterior vertices. Now we have 4. So this is this kind of tetrahedral geometry. Now the configurations that we consider, that are no longer particles, are going to be loops. So we consider loop configurations where we just occupy certain edges. Okay, and we want to consider closed loops. So here's a closed loop, here's a closed loop, et cetera, et cetera, et cetera. Right, so we have these loop configurations. Now, there's a lot more of them than there were of these point particle configurations because it's a more complicated geometry. But nevertheless, we can define these various loop configurations, and we can again demand that they're locally identical. So whenever you have like this loop configuration and this loop configuration, they're different loop configurations, but they're identical around this lower corner. And so I demand that the reduced density matrices here are identical. So we have these configurations, and now the analog of the string operators, which move, which in the T-junction process just move the anyons, the analog of those string operators will be membrane operators. So membrane operators will be operators that sort of move the loop around. So these will be shallow depth circuits of local unitaries, which basically toggle you between these various states. So all these membrane operators act on triangles now, just like string operators acted just like string operators in the previous example acted on edges which connected the central 0 vertex out to one of the outer vertices. Here, the membrane operators will act on triangles which connect, which are basically of the form 0 times 1, 4, or 0 times some some external edge of this tetrahedron. So there's 6 of these kinds of membrane operators. Okay, so the prescription by analogy with this T-junction process is pick the configurations, pick the membrane operators, make sure they're shallow depth circuits, and then simply compute this process. Okay, so here I start with this configuration, I act with this membrane operator, I get this configuration, I act with this, et cetera, et cetera. It's a 36-step process. At the end of the day, you come back to the same configuration, although note that if you keep track of the orientation along the loop, the orientation actually reverses. Even though this looks sort of heinously complicated, and I don't expect anyone to sort of really in real time figure out what this is doing, it turns out that what this is doing is something simple. It's just taking the initial loop and effectively, as far as topology is concerned, is just rotating it around the diameter by 180 degrees. That's effectively all that it's doing. But it's doing it in some complicated way. And again, that complicated way has to do with canceling non-universal phases, as you see. Okay, so this is a figure which is actually kind of a figure that I just threw in here. So there's there's actually a nice geometric way to think about the space of all possible loop configurations. This thing traverses the space of different loop configurations, and it turns out that that space of loop configurations can be given a geometry. Okay, so there's some notation here that I use that I'm not going to explain now, but basically the vertices in this geometry correspond to loop configurations. The edges, an edge connecting any two vertices corresponds to an allowed membrane move that toggles you between these various loop configurations. And this path in red is a 36-step path, which precisely represents the path defining this invariant. So the only reason that I draw this is because there's some actually nice topology happening here. It turns out that this moduli space of all loop configurations can really be given the geometry of RP2, which is sort of explicitly illustrated in this figure. It turns out that this is explicitly RP2. It turns out that this path that I've defined, computes this invariant, is actually the generator of pi1. So it's sort of the non-trivial path in the pi1 of RP2. That's actually important for proving certain things about this. But anyway, just to sort of illustrate, there's some non-trivial geometry behind this.
Sorry, it's RP2 if you if you identify loops with opposite orientation.
Yes, yeah, that's right. So yeah, exactly. Yes.
Thanks.
Yeah, I guess if I don't do that, then this is probably the double cover, which is probably just S2. Yeah. Okay, so let me sort of argue. I mean, I'm not going to give the details, but let me argue, show how one argues that these loop self-statistics are actually well defined. How do we come up with this crazy invariant? So first of all, let me just sort of illustrate the fact that the definition of this invariant sort of relies on there being membrane operators which toggle you between these various loop configurations. So let me just, which are also shallow depth circuits. So let me just show you that there's sort of at least one standard way to define such membrane operators. Yeah, I don't have to use this definition. Like the definition of the invariant doesn't care what you use as long as it's a shallow depth circuit and does the right things. But here's a sample construction. So this is kind of this idea that if I want to toggle between this loop configuration where these edges are occupied and this one, what I can do is I can sort of nucleate a loop in the bulk of this triangular plaquette and just kind of splice it into the skeleton, the one skeleton of the configuration. So I can splice it in on the edges, and then I can sort of act to remove any kind of fuzziness or dirt near the vertices. And these actions are all shallow depth circuits. This is a shallow depth circuit. This is a shallow depth circuit, which is controlled by the occupation of this edge. That can still be made a shallow depth circuit. And then this is some kind of a shallow depth circuit as well. So by composing these, you can build the right membrane operators. So anyway, so the sort of key point, the key reason why why this invariant does not depend on the choice of membrane operators, why all the non-universal phases cancel, is that any two different choices of membrane operator acting on a given configuration differ by a phase. I mean, they kind of have to. They both take one configuration to the other. They have to. If they both do that, then their action can at most differ by a phase. But the point is that phase is not an arbitrary phase. It doesn't depend on the configuration in some arbitrary way. It actually depends on the configuration sort of locally. So it depends on So this is a piece which sort of measures the configuration of occupied states, but it only probes it near vertex I. This one only probes it near vertex J, so it sort of probes it locally. So it only probes it near vertex 0. So it's a product of sort of arbitrary phases which can only locally probe the configuration. That's not the same thing as just saying, oh, an arbitrary phase that depends on the configuration. And ultimately this, we proved this in independence, but ultimately it just comes down to the fact that this is a shallow depth circuit. So this is a local object. Both these are local objects, so their difference kind of has to be local. And so using that, you can just throw this into this expression, write this loop self-statistics in terms of this modified membrane operator M prime with all these phases, and just see that all these phases cancel out of this expression. Okay, so it might seem kind of miraculous, and actually, I mean, there's no sort of good. I can't really provide any sort of good analytical intuition for why this is true. And in fact, one of the ways we found this is just by throwing it into Mathematica. So basically, we kind of wrote a Mathematica program which kind of keeps track of the non-cancellation of these phases. Yeah, Natty.
Yeah. So, is there a way of writing this process as some defect in Euclidean spacetime?
As some defect.
Yeah. So. There's a third, when you started the introduction, I did not interrupt there. There's a way of thinking about the anyons, the TQFT, in terms of defects, and this is something you understand better than I do. So this looks to me like this is a certain word line or surface line, or some process of some defect.
Yeah.
So this is something you should be able to say in the continuum using some.
Yeah, so I'll have a couple slides coming up, which I think will.
Okay, I'll wait. Okay, I'll wait. Sorry about that.
Yeah, no. Thanks for the question. Yeah, I'll definitely have a continuum intuition for this.
One more question. So these phases, they are only associated to vertices. There is no piece coming from the legs or from the.
It turns out that the pieces from the legs, you can have pieces from the legs, but they're so subsumed in the vertices. Because if you think about it, just depends on a piece from the legs just depends on the occupation number of this edge, which this vertex and this vertex both know about it. So you don't actually need you don't need that as a separate. You can write it if you want, but you don't. You can kind of group it all into one of these vertexes.
So I see. Okay.
Yeah.
I have a question. I think similar to what Nati asked. I think the question can be rephrased as: do you know the link or not invariance for this process you are describing in the space-time?
Yeah. So
can you say?
I'm going to have the same answer as I had for Natty. Hold that thought until I'll show you some nice figures.
Okay.
And you can ask a question again.
Okay.
But that is a good question.
Thanks.
Yeah.
Excuse me.
Yes.
Lucas, can you hear me?
Yes.
Yes. Excuse me. I have maybe a stupid question, but if you can solve me with that. I would like to know what is the relation about your dot row in this case with the indexes that you put, because I see that for this reason I think that it's really some stupid or so basic, but I would like to know what's the relation between the indexes that you put in your equation and the growth of the regions that you put in your.
Are you talking about this equation right here?
Exactly.
Yeah. So okay. So maybe this is just our bad notation, but the lower indices ij just refer to the fact that I'm looking at the membrane operator which acts on the 0 ij plaquette. Okay. So there's six types of these plaquettes, and then the upper index refers to the fact that I'm looking at, for that particular triangular plaquette, I'm looking near the 0 vertex. So for that membrane operator, I'm looking near the 0 vertex. I mean, these are kind of redundant down here. I guess I didn't really have to have them, but. If I once I put them in an equation that involves all the different kinds of m's, then I want to kind of keep track.
Okay.
It's not the most pedagogical choice of notation. It's just something that we can't.
Yes, because it's really difficult to follow. Because I tried to see how the relation between the geometry and the indices that you put, and trying to go from the first part of the matrix and at the last.
Okay, so let me maybe actually, I think I can maybe say it in a slightly clearer way. So really,
thank you.
Essentially what happens with this geometry, what makes the non-trivial universal phases cancel, is that every time, let's just look at the neighborhood of like this upper vertex here. So in this first move, it goes from, this particular configuration where these two edges are occupied to this configuration where these two edges are occupied, right? And so the point is that somewhere else, I'm going to find it in the figure right now, that happens in an inverse way. Okay, so when you go from this configuration to this configuration, and that's true for every vertex. For every vertex and every move, every particular move from one local configuration to the other, it always gets inverted. And so that's essentially why the non-universal phase is canceled, because like, you know, there could be some uncontrolled phase that depends on this, but it always gets inverted somewhere in the figure. And that's actually how we sort of found this path. We just kind of, we built a big array which keeps track of all these different moves and just kind of hope to get a 0 at the end for everyone. Everyone occurs equally the same number of times in the forward as the backward direction.
Okay.
And then that's probably a bit more clear way to say.
Yes, I'm sorry that I have this problem with this last understood. For this reason, I tried to follow.
Sure. I understand. Yeah.
Thank you very much.
Okay, so
also, sorry, can I ask a question just before you move on? Sure. This small one. So, because you mentioned Walker-Wang at the beginning of the talk, so that's a two-gauge theory, abelian one, and you're basically doing whiskering, right? These membrane whiskering.
What's that?
So in a two-gauge theory, a discrete two-gauge theory, you assign two holonomies and one holonomies, and essentially a two holonomy whiskering is basically like if you go back one slide, it's this operation. Well, essentially, pretty much this operation. Yeah.
Okay. All right. I learned a term I didn't know. That's good.
Yeah.
Okay. And actually, I'm also going to talk more about the Walker-Wang model in a moment. So let me press on, and maybe you can.
Okay. Yeah.
Use that again.
Thank you.
So, yeah. So here's the key thing. Actually, the really real key subtlety, which actually took us a while to realize. So we showed that this loop self-statistics is independent of the membrane operators, and then you could just declare a victory, but not quite, because we still have to show that it's independent of configurations, right? We chose these loop configurations. So for a given fixed set of loop configurations, we show that it's independent of choice in membrane operators, but we still have to show that it's independent of the choice configurations. And you might think, well, of course it is. I mean, it's just some triviality, but it actually turns out to be highly non-trivial here. And it actually turns out these loop self-statistics are not independent of the choice of loop configuration when the gauge charge is a boson. Loop self-statistics turn out to be just not well-defined when the gauge charge is a boson. They're only well-defined when the gauge charge is a fermion. So what's going on here? So basically, the idea is this. Suppose I have two different sets of loop configurations. So C is the set of all these 36 whatever loop configurations, and then C prime. So it's really the set of corresponding states in this lattice system. C prime is another set of configurations, and let me just imagine there's slightly deformed versions of C, so maybe like slightly wiggly or whatever. It's slightly different reduced density matrices. So certainly if we could find a shallow depth circuit that maps each C into the corresponding C prime or vice versa, then we could just conjugate everything. We conjugate membrane operators, and the conjugated membrane operators will be good membrane operators for the new configurations, and the computing with these conjugated membrane operators, obviously we get the same value of the loop self-statistics because we're just literally conjugating this product, which is just a phase. So if we can find a shallow depth circuit that maps each configuration to its corresponding deformed configuration, then okay, obviously loop self-statistics is invariant. So, but can we? So, given C and C prime, you can attempt to sort of construct the shallow depth circuit view by sort of first sort of cleaning up the edges. So in other words, if you're mapping C to C prime, making the edges of C look like the edges of C prime, and that there's no obstruction to doing that, and then applying some local operators that near the vertices that sort of clean up the vertices, make the vertices of this configuration now look like the vertices of C prime. But the key thing here is that you might encounter an obstruction in this sort of naive attempt to construct this shallow depth circuit. Basically, what can happen is gauge charges can get stuck at these vertices. There's no local operator that gets rid of a gauge charge. There's no local operator that does that. I'm ignoring here a problem. There's such a phenomenon as Cheshire charge where gauge charges, which are bosons, can condense on loops. But I'm ignoring that because my main interest here will be fermionic gauge charges. But in general, there's an obstruction. So really, you have to be a little more careful. So because of this obstruction, what you basically have to check is that basically you can make any two loop configurations look the same by this shallow depth circuit, any sets of loop configurations look the same up to decorating with these gauge charges. There might be some irremovable gauge charge decorations which sit on the vertices, okay? So, and those just might be irremovable. So I sort of have to check those configurations, those sets of configurations separately. And if you think about it, here's the picture. So here's my original tetrahedral geometry. I might have to consider gauge charge decoration. So every time there's a loop, there might be some gauge charge decoration on it. And so I have to look at all possible consistent gauge charge decorations, where consistent means that it's only determined by occupation numbers near the vertex, and every loop has an even number of gauge charges because it has to be something that can be created out of vacuum. And this is where the subtlety arises, because if you think about it, if you consider a gauge charge decoration of this form, this can introduce extra signs during this kind of loop movement process that I introduced. Because basically, what can happen is that, remember, you move these loops around by applying these kinds of membrane operators, but when you have these gauge charge decorations, when you sort of move between the different loop configurations, you might have to move the gauge charges along as well. They'll change as well. And so sometimes it might be that the operator which you use to move the gauge charges will fail to commute with the operator that you used to, the membrane operator that you used to move the strings. Okay, so there's this kind of braiding phase that might creep up. Furthermore, if the gauge charges are fermions, there's an additional phase that might creep up, which just comes from exchanging these fermionic decorations. Okay, so this is actually a complicated thing to check. Now it turns out, this is sort of finite combinatorics. There's only 5 vertices here, so that you can sort of solve for what the consistent gauge charge decorations are. And it turns out that up to shallow circuit equivalent, there's exactly one non-trivial gauge charge decoration. So you only have to compute these loop self-statistics, how they change for just this one particular decoration. And so we do this very explicitly.
I have a question of an ignorant person. What is this phrase you always use for the equivalence?
Which phrase?
You use a phrase. You always say up to equivalence.
Up to right, up to shallow circuit equivalence. Is that
what is?
So
shallow. Yeah.
Finite depth circuit. So
Okay, thank you. Got it.
I think that's like the more proper way of saying finite. I used to say finite depth circuit, but Zhengwan told me that shallow depth circuit is like the way to say it.
Okay.
Yeah, because everything's finite in principle, right? But this is shallow, so it's sort of small compared to thermodynamical. Yeah. So. Yeah.
Lukasz, and why couldn't you just annihilate the charges in pairs?
You can, but you have to do it there has to be one circuit that does it for all configurations. And it turns out that's not always possible. It turns out there's precisely one sort of modulo that kind of attempt to annihilate in pairs. There's precisely one non-trivial decoration. And I'll tell you what that decoration does in space-time, actually. So there's a space-time picture that Natty was asking me about, which I'm about to get to.
Since I interrupt, yes. I have another question.
Yeah.
The starting point or the motivation was to explain or to give another perspective of the W2, W3 anomaly.
Yes. Mm-hmm.
Now, that does not need additional global symmetries or decoration or gauge symmetry and so forth.
Correct.
Shouldn't you just have something which is intrinsic to the geometry without all the extra stuff?
Yeah, so this is a baby step. So all I'm doing right now is showing how to diagnose, how to diagnose an anomaly in a lower dimension, in 3+1 dimensions, for a certain model with intrinsic topological order, which is this fermionic gauge theory. Later, I'll bootstrap that into the 4+1D W2, W3 model, but I haven't done that yet. So I'm just, this is just kind of me.
My question is about the 3+1 dimensional system.
3+1, okay.
Yeah, so in 3+1 dimension, like this all-fermion QED or this SU2 with the whatever isospeed 3/2 and various other theories, they do not have any additional global symmetries.
Yeah, and I don't have an additional global symmetry here either. This is just fermionic toric code. There's gauge charges, but there's no additional symmetry.
Well, the toric code has more symmetries. Maybe they're not important for what.
Yeah, they're not important. Yeah, exactly. They're not important. I'm not.
So you're not using these symmetries.
Yeah, exactly. The only thing I'm using is the fact that I can move these fluxes and move these gauge charges, which are just the deconfined excitation of this theory. I'm not using any global symmetry. Absolutely. Yeah.
So can I rephrase what you say earlier in this slide about this gauge charge decoration?
Yeah.
Are you trying to decorate some 2D worldsheet with some 1D wall line? 2D worldsheet is a gauge flux loops wall line.
Hang on for one slide. I'm
Okay.
desperately trying to get to this slide where precisely I'm going to show you a decoration of a 2D worldsheet with 1D world line.
I see. I think I even want to ask now, are you just trying to describe the self-intersecting point of a 2D worldsheet, two of them in 4D, and there's some intersecting point, and you will call this self-intersecting? Or maybe it's not.
It's not related. It's not exactly that. We thought a lot about these kinds of geometries. There's a little more to it than that, but that's sort of one of the ways we were.
Because it seems not easy to me to imagine what exactly is this.
Yeah.
Okay,
it's not exactly that. There's a little more data that goes into it. Okay, let me just very quickly say that just get to the punchline and get to a slide that maybe Natty will like more. Computing this invariant, this loop self statistics for this decorated set of configurations, I said that there's these two signs. One from the fact that these string operators, the string operators, I guess, S03 in this case, anti-commute with certain membrane operators, and we check it for this one non-trivial decoration. We get a -1. In the case of fermions, when the gauge charges of fermions, there's this exchange sign, which turns out to also be -1. So the key point is that this loop self-statistics is only defined if the gauge charge is a fermion, because if the gauge charge is a boson, you just have the first contribution of the sign, but not the second. And so the sign is not well defined. The decorated configurations and the original configurations don't give you the same answer. Now you might say, oh, just define your invariant using the non-decorated configurations, but there's no invariant meaning to that. So in general, on the lattice, if I just give you sort of the, just the data of okay, there's some loop excitations and some particle excitations, there's no invariant meaning to a loop excitation being or not being decorated. It's only a relative thing. So really, you can't just say that. So the point is that for the case of fermions, there's a subtle cancellation between these two signs, and the invariant is well defined. It doesn't depend on decoration. And this is obviously related to this work of Theo Jones and Freud, who showed that for fermionic Z2 gauge theories, there's actually two non-trivial ones. This is presumably just a way of measuring that invariant on the lattice. But let me get to a picture that I think is more of a continuum picture. So here's more of a continuum picture. So this process, all it really does is, if you think about it, it just rotates this loop by 180 degrees. So Yuan, yeah.
I have a quick question. Does your sign depends on the framing? So you need to shift your vertex slightly in one direction and try to see which membrane cross with your gauge charge. So does this choice affect your final sign?
Absolutely not, because everything else can be taken up by can be accounted for by shallow depth circuit equivalents. So the point is that the only obstruction is the existence of this gauge charge, and I can move it anywhere I want, right? So the only thing that I can sort of not get rid of using the shallow depth circuit equivalents is the fact that the gauge charge exists. I can move it anywhere I want. That's not a problem. I can do that using shallow depth circuit equivalents. I just can't, I can't get rid of it completely. So just from that fact, that it's not going to depend on which way you offset it. Offsetting is just sort of a convenient calculation.
Yeah. Thank you.
Yeah. Okay. So here's a space-time process. So here's sort of a very schematic. So everything that I sort of just talked about now happens here. So I have a loop and it rotates by 180 degrees effectively and changes the orientation. And I wanted to make it into a closed surface. So, I imagine sort of nucleating a pair of these, rotating one by 180 degrees and then closing. So I have a Klein bottle. This is a Klein bottle. Now this decoration that I talked about, okay, so the world sheet of this loop is two-dimensional. It's a Klein bottle. The decoration I talked about is some one-dimensional decoration. And the non-trivial charge decoration, this non-trivial decoration that I've talked about, has the property precisely that this charge, there's an odd number of times that this charge winds around this loop during the process. And it's actually dual to the first Stiefel-Whitney class of the Klein bottle. So that's the continuum picture. And so the point is that, more generally, if you decorate, if you decorate your loop excitations with, we showed that if you decorate your loop excitations with gauge charged fermions, statistics is this loop self-statistics is well defined. It doesn't change. But of course, if you happen to have a gauge charged boson around and you decorate it with that in this sort of non-trivial way, or a neutral fermion, then the loop self-statistics is not well defined. And in fact, does change. These two processes are off by a different sign. And so this is actually why this relates to why this fermionic toric code that you get by Higgsing down to a Z2 gauge theory from this Allfermion QED, why it has this non-trivial value for this loop self-statistics. Because essentially you can think of it as sort of an ordinary fermionic Z2 gauge theory decorated by a neutral fermion. And then the neutral fermion decoration is what gives you this -1 contribution to the loop self-statistics. And what is this neutral fermion? Well, this neutral fermion is simply the monopole that's now sort of confined in this way. So basically the idea is that, when you Higgs down to a Z2 gauge theory, your loop excitation is simply a pi flux excitation. It's a half of the allowed flux quantum. It's a pi flux excitation. And when you do this process of rotating by 180 degrees, you reverse. You go from pi to minus pi, which means that you have to bring a monopole around once, or in general, an odd number of times, to get back to your original configuration. So if that monopole is a fermion, that gives you this, this is a non-trivial decoration, and because you have an odd winding, and it gives you this extra -1. Loop cells change loop cell statistics. Yeah, Juven.
Yeah, Lukasz, thanks very much for this slide. Very interesting. Just want to make sure my understanding is correct. Can I say the 2D worksheet of this Z2 gauge flux loop, if it's unorientable, then the orientation reversing, there should be some orientation reversing one-dimensional line. Then this wall line will be fermionic.
Yeah. I mean that's basically that's the same thing. I mean, we're just trying to we're just trying to give a lattice interpretation to that
great
theory thing that you understand very well.
Yeah. And also, I think your statement also agree that such a orientation reversing wall line does not carry the Z2 gauge charge, which is another fermion wall line.
Exactly.
Yeah, very good. I agree with this. Yeah, thank you very much. Yeah, same as my understanding. Thank you.
Okay, good, great. Okay, so let me just summarize the properties so far. I know that I have to end, so let me just go through the rest of the slides very quickly. So we have this invariant which we called mu. It's a well-defined invariant of 3 + 1D fermionic Z2 gauge theories. We can actually prove that it's always plus or minus 1. I didn't sort of say how to do that, but it turns out that it's related to this RP2 geometry, the fact that this path is a non-trivial generator of pi1 of RP2, and if you double it, it turns into a trivial generator. Or it turns into a trivial path, rather, trivial path in homotopy. We can also show that modulo some physical assumptions, any standalone 3 + 1D model must have mu equals +1. So this is really, the fermionic Z2 gauge theory that has a non-trivial value of this loop self-statistics -1 cannot live just in 3D. Okay, this is modulo a certain physical assumption, namely that any 3 + 1D invertible phase of fermions against a gap boundary, which is a non-trivial physical assumption. I mean, it's true, but it's not something that you can sort of rigorously prove. Which basically means that this fermionic Z2 gauge theory with mu equals -1 has to be anomalous. It can only potentially exist at the boundary of 4 + 1D. So the last thing that we did was actually build this 4 + 1D lattice model that hosts this anomalous fermionic toric code. So this is the invertible W2 W3 phase, we argue. It's certainly a non-trivial phase. Well, okay, let me tell you what the properties are. So, before I go into the details. So what we did was we used this Walker-Wang methodology to engineer a lattice model in one higher dimension that exhibits this whatever prescribed surface state that we have. So this is a very sort of well-known construction or set of techniques within, sort of lattice model building that basically any kind of surface that you have, any kind of surface theory that you want to realize, you can realize at the boundary of a one higher dimensional exactly solved lattice model, and there's sort of an algorithmic prescription almost for how to build that model. So that's what we did here. We kind of said, okay, we want to realize this fermionic toric code with -1 self-statistics at the boundary of one higher dimension, and so we just built a Walker-Wang model from that. And basically what we did is basically the general prescription for building such a Walker-Wang model is that configurations in this Walker-Wang model, it's a model in one higher dimension, should be thought of as space-time histories of the various of the processes that can occur in the surface theory. So this Walker-Wang model that we did build has a fermionic charge, bosonic loop. No, it's supposed to be a fermionic loop. Sorry, misspelling. So it has a fermionic charge and a fermionic loop, which means that, first of all, in terms of sort of processes, it means that the charge braids non-trivially with the loop. So that tells you that you get a -1 for configurations where the loop world line links around the charged world sheet in your 4 spatial dimensions. The charge is a fermion, which in the Walker-Wang sort of world is incorporated by including a sign that's like -1 to the framing, where the framing is given by choosing a certain projection. And the sort of non-trivial fact that the loop is fermionic, the sort of new thing here, is basically what Juven was just talking about, which is just that you pick orientations on all your plaquettes, and anytime the world sheet, you look at your world sheet, anytime the orientation changes, you decorate that with effectively a neutral fermion. So that's a well-defined sort of prescription for building a Walker-Wang ground state and a Walker-Wang Hamiltonian. Anyway. I don't want to, since I'm out of time, I don't want to sort of go too much into this, but let me just very clearly state what the properties of this 4+1 dimensional model that we have. So we can, it's a model. We can show that this thing is explicitly disentangleable if you have 2 copies. So 2 copies can be disentangled in the product state. So that immediately shows that the model has no anyons, because if it did, then 2 copies of it, once you apply to unitary, would still have anyons, and that the product state does not host anyons. So we can explicitly disentangle 2 stack copies, which immediately shows that it's a Z2 invertible phase. We can show that, basically by construction, it admits this 3+1 dimensional boundary with the fermionic charges in Z2 gauge flux loops, and that the loop self-statistics is -1, sort of by design. Okay, so this is almost rigorous proof that this thing is a non-trivial invertible phase in bosons in 4+1. And okay, so that's all I wanted to say. Here's some sort of conclusions and future directions. But since I'm out of time, let me just sort of leave this slide up and take questions. Thanks.
But you do have another 25 minutes.
Oh, really? Sorry, I thought this was an hour.
No, it's 90 minutes, but you do have time to explain more. And also you haven't answered the question, Nati, and I asked, what's the space-time picture of the braiding loop braid, self-braid, whatever loop braiding process you are talking about?
Okay, so the space-time picture is just back here. I mean, it's literally this. It's a Klein bottle, right? Because the space-time picture is literally just this loop rotating by pi. Okay, so the only subtlety is this cancellation of non-universal phases. It's just like saying, the space-time picture of seeing the -1 from fermion exchange is just just this process that exchanges the fermion. So the obvious thing is just the infinity shape. But that doesn't tell you how to do things on the lattice. You still need this complicated T-junction process to cancel non-universal phases. So the space-time process is simple. It's just literally rotating this loop by pi around the diameter. That gives you a -1. So that's the loop self-statistics. That's it. But to actually make sure that that's well defined on the lattice and all non-universal phases cancel, that's why we need to go to do all this complicated stuff with like the 36 steps. Does that make sense?
Okay, and this statistics is from the loop.
Yep.
Which is a 2D worldsheet, and that fermion is the neutral fermionic.
Yeah. So the neutral fermion
neutral to the Z2 gauge theory, Z2 gauge charge.
Well, so the neutral fermion that decorates the orientation domain well, I mean that's sort of I don't need to talk about that in order to define the loop self-statistics. Loop self-statistics is really, this gives a minus sign. That's a picture. That's a picture for how one would construct a model, decorated model in which this is -1.
Okay. Yes.
It looks like 2 participants raised their hand, but I don't know who it is. So anybody?
You can go first, and then Mauricio next.
Yeah, thank you. So Lukasz, it's a very nice talk. I have 3 questions for you. Yeah, sorry, it's very long. Okay. So the first one is, do we really need a charge to define a string statistic? Like if I'm given a theory with only string excitation without any charge, we can still define a statistic, right?
Yeah.
Okay. Yeah. Because my example is like the B is a 2-phone, like a B sin row 1B. So I believe on the boundary of this 4+1D SPT, it should have some fermionic spin excitation. So I can still apply your invariant to this model, correct?
Yeah, I mean, my only point about the charges was that if you happen to have charges, point-like charges in your theory, you just have to check that they don't mess anything up, so that the invariant you define, is not affected by these charge decorations, because it's having a charge decorated loop and a non-charge decorated loop. There's no sort of a priori way to distinguish and to say which one's decorated, which one's not. So you just have to very carefully check that the charges don't mess anything up. The charges are not involved in defining the invariant. The charges are just there. The only way that the charges come in is just checking that they don't mess anything up.
Okay, thanks. Yeah, and my second question is, how do you show your construction is literally the W2, W3? Can you apply a path integral to obtain the space-time action for your model? Or you verify this property, okay, it matches with W2, W3. So you claim your Hamiltonian corresponds to W2, W3.
Yeah, no, we didn't. So basically, we constructed a non-trivial. We constructed a phase in 4+1D. It's invertible. It's Z2 classified, and it realizes something that can be obtained from Higgsing the all-fermion QED. So actually, so that there in particular, it means that it can realize all-fermion QED as well on its boundary. But we didn't like. I think you could do this, and I think you guys did something like this, right? You actually can put it on space-time, and you computed W2, W3. I think that's very nice. I think. I just like to think on a fixed lattice. Somehow this notion of putting a general lattice Hamiltonian on the non-trivial spacetime always worries me, because there's all these ambiguities onto how do you actually, how you actually put things on. But I think there's just, I think what you guys did is very nice, and I know you told me about this. So.
I want to show our model are actually in the same phase. Yeah. So for example,
I'm sure it is. I'm sure it is. Yeah.
Oh, yeah. Do you know how does your process look like in the 3D cubic lattice? The 36 state, can you
okay. We worked on a generalized triangulation, and so we defined our model on a general triangulation. I mean, Zhengguan wrote the model in the general triangulation. So we don't have an immediate picture on the cubic lattice, and we could try to write one down. But I know you do, and I think it's probably.
I only have a model on cubic lattice. I really want to verify my spin operate can give a mu equal to -1.
I'm sure it does, but yeah, that's something you need to do. Yeah.
Yeah. Thanks. Yeah, that's all my question.
Okay, great. Yep. Who's next? I can't see who's next. Juven?
Okay.
Mauricio.
Okay.
Hi again. Well, I have some questions about, some possibility of finding some relation with your result and possible extension of it. Well, first of all, I would like to, if you can go to the next page of slide, please.
This?
Yes, in this part. No, in this part, naturally. You define here the trajectory of the monopole in this case, and as a fermion field.
Yep.
And I am with Gauss charge in this case, but I would like to know, for example, yes, in terms of electrodynamic or by some experiment, if you can extend this result, assuming that the trajectory of this particle is not necessarily a monopole, but a multipole. In this case, if you can describe it like a dipole or quadrupole or octopole and so on.
Yeah,
physically, it's a little weird, but I'm not sure if you can extend that and try to find other type of changes of chains to describe other type of problem, preserving the idea of that this problem is technically a fermion.
Yeah. So I mean, in this case, if you look at this process, it reverses the orientation of this, the direction of this flux. So you need an odd number of monopoles to go around. So you can certainly have a bound state of an odd number. Any odd number is fine. People have asked me about extensions to like Zn rather than Z2, and whether there's something with Zn. And in that case, you can imagine more complicated things, although I don't see how the monopole picture would fit in there, because I guess Zn means, go from +1/n to -1/n, that's 2/n, that's still a fraction. So, okay, so basically, I mean, I think the short answer is I don't know.
No, but my idea is now, if you can imagine, but for example, because I don't know if you did, for example, if you try to compute some case, but what happened if you try to do the same, for example, for the next step at the pole, for example, if you try to do the same, but not with a neutral fermion, but a fermion who can be described by the at the pole, not necessarily a monopole like this form, this classical way.
Sorry, not a monopole, but what?
Dipole.
Dipole.
Dipole. Sorry.
Okay. I see what you mean. Okay, that I don't know. That's a good question. I don't know.
Okay.
I mean, I know people look at dipoles and but okay. I mean, yeah. The thing is that we spend most of our time thinking about just the Higgs version of this thing, right? So it just goes down to Z2, and the only role that the monopole plays is just turns it pi to a minus pi flux. Dipole in the Higgs that plays no real role. So that's okay. That seems to answering that question seems to like require just getting a better handle on this compact QED, all-fermion QED itself, which I don't really haven't spent a lot of time thinking about. But
okay,
good question.
Okay. My second question, well, I possibly will answer with that. It's associated with your manifold, which your company manifold that you are describing all the process. I am not sure if your result in terms of Gaussian 2 can be preserved if you study with other isomorphic surface. In this case, if you extend the dimension or if you preserve the dimension, whatever.
Sorry, which manifold are we talking about? This or the manifold that
because you are working with the Klein model, yes? And
that's the manifold described.
The Klein model is isomorphic to other type of manifolds that are compact and everything like that. Okay, suppose that you have the same trajectory of your fermion with the as a monopole, and you try to do the same, but with other type of geometry or other type of topology that are isomorphic to this part. I'm not sure if you preserve the same result or you have other type of transformation that doesn't preserve. And by this case, if you have some idea about how other algebras that you can study from this case. I'm sorry, maybe I am going out through the problem, but it's just a curiosity about your explanation.
I mean, I could say a few things about these kinds of world sheets, because we actually spent quite a bit of time thinking about sort of the continuum version of this and sort of various world sheets that you can embed in 4D. There's quite a bit of geometry here that we ultimately didn't make it into the paper, but kind of was useful in terms of sort of intermediate stages. So any Klein model, anything that's isomorphic to a Klein model will give the same result, but you can ask about sort of other manifolds. And for instance, like one space-time history would be an RP2. That's certainly a valid surface. And so for the case of RP2, it turns out that there's a sense in which that will give you plus or minus I. Just like this non-trivial Klein model gives you a -1, the RP2 will give you plus or minus I. But whether it's plus I or minus I is very subtle. And it has to depend. It depends on sort of some additional data, which is this choice of framing. So I'm not sure I can say anything intelligent about sort of more generally, but I will just say that I think we do have a pretty good continuum handle on how to assign these various phases to sort of various world sheets that you can embed in 4D.
Yes. Yeah, thanks very much. I think time is limited. Let's Max. Yes, Max, please go ahead. Thanks.
Yeah, I had a related question to this picture. So I guess for just in 2+1 dimensions, if you braid anyons, if you do it in continuum, right, then you actually need to assign framing to the to the trajectory. So I guess strictly speaking, when you draw this Klein model, you also need to frame it.
Yep, absolutely. Yep. And that took us a long time to figure out. and I mean, we kind of knew it, but it just took us. Yeah, we at some point we were trying to assign. I don't know why, but we were trying to assign actions to unframed surfaces, and like we got something trivial at the end. It's sort of it took us a long time to realize that no, you need a framing, and the framing is it's not quite the same thing as a framing because there could be singularities. So it is additional data that's like a framing. Basically, it comes from projecting down to 2D. But the problem is that there could be certain singularities that you have to deal with, which you don't have for sort of the blackboard framing in 2+1D for trajectories in 2+1D. There's no singularities, no problems. The framing is well defined. Here, if you just take a generic projection down to 2 dimensions from a manifold, if you have a surface that's embedded, 2-dimensional surface that's embedded in 4 space, and you project down to 2D, you will have generic irremovable singularities. So you will not get a well-defined framing, and there's no sort of small perturbation that you can do to get rid of these singularities. They actually have to be canceled in pairs. So there's sort of pair singularities that you get on these surfaces. And we thought about this for a long time, and for some reason, I don't know, it really helped us think about this. Ultimately, design the lattice model, but somehow it didn't make it into the final version of the paper.
And in 2+1D, when you change the framing, right, the answer also changes. I mean, in fact, the theta, right, the topological spin is kind of what you get by changing. Is it similar here or not?
Yeah, that's right. So the answer will change if you change the framing. Yeah. Mm-hmm. Yeah, absolutely. Yeah, I mean that's right. It has to. I mean, because otherwise the framing is not really doing anything. But it has to do something.
Sorry, what change on the framing? Just make sure I follow.
Well, it's just in 2+1D, the answer that you get for your trajectory depends on whether if it's a fermion, a closed loop of fermion, it depends on whether it's the framing winds an odd number or even number of times. So here, the answer does depend on you can have an answer that's let me think. Yeah, you can have an answer that's +1 or -1 even for a Klein model, but it just depends on this extra data of framing. But now I'm actually not entirely. I don't entirely remember how this jives with the decoration picture. I mean, I guess both the decoration and both the decoration and the framing are determined using this projection, I think. Sorry, Max, I don't want to say something incorrect. I'm kind of forgetting the details right now, but broadly speaking, what you asked is that things do depend on the framing. So,
no worries. Thank you.
Yeah.
Thank you.
Yep.
Okay, Hank.
Yeah, I would just like to thank you for the very nice talk, because if I understand the sort of the components of this bold M operator that you constructed as whiskering of 1 holonomies by 2 holonomies, then essentially the result is that you can actually use a bunch of whiskering moves, like a series of 36, I believe, right? Yeah, like these series of whiskering moves on the lattice to detect the framing of these loops.
So is whiskering, is that a math term? Why haven't I heard this term before?
I'm not sure. It was I think it was coined by a paper by Bolavant on cross module gauge theory based on cross modules.
I see.
So it's if you go back to the picture with the triangle, it's exactly that, where you have a holonomy here, and then you just push it towards one of the vertices on the other side.
I see. Okay. So you say, sorry. Who can you tell me the name of the author again?
Yep, I will.
Or type it into the chat maybe.
And the author is, if I remember correctly, one of the authors is Bolavant. Yeah.
I see. Okay. Thanks. Yeah, that's good to know.
Yeah. So
I had no idea.
So the other, my question is, have you thought about triple loop braiding? So,
okay, this looks like that's exactly the same question that somebody wrote on the chat.
Oh.
Like three loop braiding.
Yep, that's right.
Yeah, so we of course thought about 3 loop braiding, but it didn't seem to capture this. This is really a loop exchange process.
Yes.
It just 3 loop braiding. I mean, there's an obvious thing you can try. like to make 2 of these loops framed or whatever, linked with a third base loop and do exchange. But doesn't capture this invariant. We've spent a lot of time thinking about this. It just doesn't work.
Yeah. So I think this is a self-braiding of loops, right? And
Yeah,
the three
or self-exchange or whatever.
Yeah. Okay, I see. Great, thank you.
Yep.
I do remember Ryan's paper in 2014. He did draw the through braiding, but I didn't follow that part. Is there anyone know?
I didn't follow that part either. I've talked to Ryan about it a little bit. Yeah, we found aspects of that paper very useful, but there were parts that I'm still not sure whether they're sort of the same or different.
Okay, thanks.
I don't want to comment on something I don't understand.
Okay, I didn't understand that part. Okay, thanks.
Yeah.
Also, one comment is that I read a paper by I forgot a name, but they say that bosonic 3+1D topological phases are characterized by the triple loop braiding statistics.
Yeah, but this is an anomalous phase, right? So you have an out. It's not really a 3D topological phase. It's a boundary of 4D. So you can just say, well, it's anomalous, and so therefore.
Yeah, that's fair enough. Yeah, that's sort of like a different setting, but.
Zhenbi.
Yeah, I just have a very naive question. I'm just looking at these figures. How do I understand this as a self-braiding? The starting point and the end point doesn't seem to be the same.
Well, sorry, there's one more move you have to go from here to here. So it's apply M34 inverse, and M34 inverse will sort of move the loop, move from here to here, and it ends up here.
Sorry,
I just didn't, I didn't have enough space to like fully draw like all the arrows. I should have drawn one extra figure here. Yes, sorry.
All right, thank you.
Yeah.
Yuan has another question.
Yeah. Sorry for too many questions.
No worries.
Yeah. So usually when we think of a fermion, it's like we have the wall sheet and we couple to the W2.
Yeah.
So it's the definition of fermion. And for the fermionic string, it's like we have the wall sheet. So originally it's a one line. We found a wall sheet and we couple to W3. So this is the definition of the fermionic string. So how does this definition relate to your process here? So is it a direct connection?
Can you answer that for us?
This is my question. I'm curious, like how this definition of W3 related to your process here.
Yeah, I'm also curious. So.
Okay.
Yeah. I mean, I'm being a little flip, but yeah, I mean that's a great question. I there should be some. I mean, yeah, I don't know.
I think Yuan's question is that it may be obvious from the path integral or Lagrangian point of view to write down those terms, and how do you see this in the Hamiltonian picture?
Yeah, I mean, right, yeah, exactly. I mean, I don't know. I mean, like it's one of those things where, like, in the Hamiltonian picture, we kind of did the only thing we could, and we came up with this thing. And certain things might just not be directly expressible in a Hamiltonian picture. Like maybe this is the only thing you can do in a Hamiltonian picture, and it is in principle a reflection of this W3, but like W3 by itself doesn't sort of make a direct appearance somehow. I don't know. I mean, I don't know.
I see. Yeah, because the Poisson and I, we use a different strategy. So we use the property the W3 equal to dW2 divided by 2.
Yeah, I think, yeah, right, good. Yeah, so that somehow makes connection to this orientation reversing.
Yeah, so we consider the positive string and the positive membranes and negative membranes, and we consider their boundary, and we try to detect the boundary line has some fermion property.
Right. Oh, whoops! I think I accidentally paused sharing. Sorry. Sorry. Oops.
Okay, so I think maybe we should thank Lukasz for the wonderful seminar. Thank you very much.
Great. Thanks, Julian, for the invitation.
Thank you very much.
Appreciate it. Yeah. Take care. Thanks. Bye.
Thanks. Thank you. Bye-bye.